All right. Well, thank you very much once again, Celine, and everyone in the EAGE committee for inviting me to be here and present today. I'll start with a short disclaimer. In this presentation, we will not see very many geophysical applications and pretty seismic images, but hopefully what you will see is still exciting because you will see some, or I will talk about some of the technologies and software that power nowadays most of our geophysical processing, imaging, and inversion algorithms. I will say PyLops as kind of a way to explain how we nowadays solve large-scale geophysical inverse problems. And actually, this goes beyond geophysics. But as part of the disclaimer, I like to say that there are similar frameworks in other programming languages. So don't take PyLops as the only ground truth in this landscape, but hopefully I'll convince you by the end that this is the right way of solving inverse problems, and this is one framework, especially if you use Python, that can help you go a long way. So before I can get into the details, although I expect most of the audience to have some knowledge of inverse problems, I want to take you for 5 minutes back to 101 inverse problem, what you did probably in your master degree, and try to make sure we are all on the same page. So what is an inverse problem? In simple terms, no matter which field of science you are working with, we have a set of model parameters that we are interested in. Could be subsurface properties, could be tissue stiffness in a human body. But these are parameters that we cannot sense directly because it's either too expensive or dangerous. And so we have some observations that could be acoustic measurements, elastic measurements, electromagnetic waves, or any type of other remote sensing measurement that we can instead acquire. And we have a relationship between the two. That is what we know through our knowledge of physics, generally comes with some equations or PDEs. This is what we call a modeling operator. Now, in many cases, this problem can be linearized or is already linear. And the reason I'm showing you this with the matrix G is because PyLops tackles linear problems. But as I said, even if the problem is non-linear, many times in geophysics and in other fields, we tend to approach the problem as we linearize, near a solution, we then solve the linear problem, then we linearize again. So anything you'll see today will be either used directly to solve the problem or used in an inner-outer loop to solve a nonlinear problem. All right, so this is pen and paper. If I have a vector M with some numbers, a matrix G, I can compute my data D. I can compare it with the observations, the real observations. And again, if we stay in this 101 inverse problems class, you'll probably remember that there are ways to formulate the problem such that you minimize the difference between the model data and the observed data, what we call the residual, and then you get this closed form solution. That is nice because you can write in a single slide and pretty much tells you that if I take this matrix and I transpose and complex conjugate it, this is what this H subscript stands for. And I also apply G, H to G, and I invert this matrix, then basically what I can get is my closest estimate of the model in terms of minimizing the residual. Now, why pen and paper? Because this in practice can almost never be done in real life for two reasons. G is generally too large. There could be problems in storing it. There will be problems in moving it around if you solve the problem in a distributed manner. And also applying directly G as a dense representation of your modeling operator to M can be too expensive. So this is where the idea of matrix-free optimization comes in, and PyLops is leveraging it, but this is not an idea that comes from us. It's a very well-known idea in the applied mathematics community, and all of the other libraries that I mentioned previously, they tend to leverage this idea equally well. And the idea is as simple as follows. I will later come back with an example, because with an example, I think these things become a bit more easy to grasp. But in a very high level perspective, all I need to do, in this case, I need to be able to write a piece of computer code, a function that takes this vector M, it applies a set of instructions, it returns a vector Y, which is equivalent to being able to have this dense matrix G modeling the physics of my problem and applying it directly to the vector. I will also need to be able to, and you have seen it previously, why? Because when you want to find the inverse, you need to be able to compute and apply also the adjoint of these operators. So I will also need to be able to have a second piece of code or a function that takes now a vector D. It applies a different set of instructions and returns a vector X, and will be again equivalent as if I had the matrix. I will transpose it physically, apply complex conjugation to each element, and then multiply to the vector D. Now, if you take this pair of functions, and you put them together for whatever modeling operator you would like to use to solve your problem of choice, and you combine them, what you are basically doing is what I mentioned previously, is so-called matrix-free optimization, because any iterative solver that you can think of that we use nowadays to solve these large problems, any iterative solver requires only you to pass a function that applies the forward, a function that applies the adjoint, and the solver could work equally well, produce the exact same result that if you really had this dense matrix and you'll ask the solver to apply the actual dense matrix vector multiplication. So from a very high level perspective, what PyLops is a Python framework that provides these two main ingredients, provides a bunch of modeling operators. I'll get a bit more into the details soon. So each modeling operator that models different physics has these two functions, this matvec and rmatvec, that perform the forward and the adjoint, and then provides a suite of solvers, because if you cannot really solve an inverse problem, things are not very interesting. Yeah, you could take a model, try to apply the operator and see how close it is to the data, and then randomly change the model. But that is going to be, again, way too expensive in real life. And so by combining these kind of two ingredients, we can solve almost any problem of the form that you see above. A problem that has a main data misfit term, so what I mentioned previously, the difference between the data and the model data, or the residual, and then any regularization or prior information that comes from our knowledge of what we would like the solution to look like. We like to look like smooth, like to look at sharp, we like the solution to look like a sum of some basis function in whatever domain of choice, or we know that a solution should be bounded between some maximum and minimum numbers, for example, driven by physical understanding of the problem. A bit more in details, if you look at what PyLops is nowadays, this is a library that started 8-9 years ago for fun. That was pretty much just me. And then through time has evolved in an ecosystem of tools that now has quite a few developers behind that develop it on a, say, weekly basis, not daily basis, and then a lot of people that have contributed more or less through time. So what we provide basically is a very large, extensive set of operators, is nowadays 50 plus, and the possibility to combine them. So sometimes you'll discover, I'll show you an example, that a problem could be constructed by combining already existing operators, not having to rewrite a new operator from scratch. So having many operators and the possibility to combine you kind of gives you more combinatorics than just, you can't solve just 50 problems, you can probably solve a few hundred problems because of all the combinations you can make. We then, as I mentioned already, provide solvers, otherwise you can't really solve a problem without a solver. If you are in geophysics, you'll probably know that geophysicists love sparsity. So they love to represent their signals in some transform domain where just a few basis functions can explain the signal, and we provide a fairly extensive set of sparsity transforms. Back in 2017, 2018, when I started this project for fun, deep learning was still kind of a niche area, but through time, nowadays, probably everyone here has been doing a pet project or working daily with deep learning. So everyone wants to be able to do deep learning. So we provide an integration with PyTorch, the most popular framework for deep learning. So you can take PyLops operator directly into PyTorch, not having to implement all of them natively in PyTorch if you want to solve a problem that has, for example, a physics operator that you already have in PyLops. Since we don't like to make favoritism, we also created an integration with JAS, so the Google equivalent kind of framework for deep learning. Recently, one of the main core developers also created a small integration with PyMC3, which which is the most popular library for statistical modeling, for example, Monte Carlo Markov chains. So again, you don't need to implement your operators there. And then I'll talk a bit about later in more details. We also provide integration with MPI, the most common paradigm or communication library for distributed computing, so we can solve problems on multiple nodes and supercomputers. All right, so one last slide about the overall idea of PyLops, and I'll start to get a bit more in details. You may say, okay, is this library being used by someone but me and a few of the other core developers? We have what I call declare users, is basically mostly universities, because they're not afraid of saying that declare users, and they're people that have been using it and writing papers and acknowledging it. And then on the other end is colleagues and friends that work in these other companies, I'm not going to name them, that have told me through times that they're using it, and I'm going to make a disclaimer. Apart from my company, where I'm not going to say anything, but all of the other users, they never said that they're using it in production. It's mostly a research tool. Okay, so from now on, I'm going to go a bit more into the details. And generally, when I present, give a presentation of this kind, I tend to divide it in 3 parts. The first part is sort of for beginners, how you could get started. The second part is a bit about the flexibility, trying to show examples why this library is not used just by a few people in geophysics, despite most of the core developers are actually geophysicists. But the fact that it's fairly flexible and extensible has been really key for people in medical imaging, telecommunication. And nowadays, I know people have been actually collaborating in DAS companies that are using it. And then finally, I'll talk a bit about scalability, which is something that came through time. The origin of this framework was mostly educational for, in a way, university scale. And then we saw the potential and we made it a bit more scalable, Now we can say that it has run problems multiple times in some of the biggest supercomputers. So both in my previous organization in Chaos, as well in some of the US national labs, we have been using it for various research projects. Okay, so since I would not have time to go deep in all of them, I decided there is a lot of resources, and I'll pointing to you for the first part. So I'll just give you a glimpse of the basics, and then I'll try to give you a bit more on sort of deep dive into more, I would say, interesting aspects. So, but I promise it, so I'm going to do it. It's going to take me a few minutes. What does it mean taking a matrix or a linear operator and not just forming the matrix and applying it to a vector? Why we want to go about this complexity or making an equivalent function that will be equivalent to having a matrix? If I can make a matrix, why would I not make it? And the easiest example that I can ever think of to make this point clear is element-wise multiplication. Imagine you have 2 vectors and you want to multiply element by element. And if you have done linear algebra, you probably know that the equivalent operation to element-wise multiplication is to build a matrix that is a diagonal matrix where you make the element of the main diagonal being equal the coefficients of one of the 2 vectors. And then when you multiply a matrix of this kind to a vector, it is equivalent to do element-wise multiplication. You could do it by hand. You will see row by column, row by column, row by column. So here already you can see 2 things. So first, why would you not just make this matrix? Because if the problem is not 3 by 3, but is 1,000,000 by 1,000,000, you have a lot of zeros that you already know by construction they're there. And it will be silly to apply a lot of 0 times something multiplication, which your computer doesn't know, so they're flops. Instead, it will be much easier to wrap these into a function, as I mentioned previously, and just apply element-wise multiplication, which will be only n operations. The second thing that you can see is, I said you don't need only a function that applies the matrix multiplication, but also need one that applies the adjoint. Okay, how do I build the adjoint? Generally, what I tend to do, I tend to write whatever operator I need to tackle, small pen and paper, perform the adjoint operation pen and paper, and then recognize how that matrix looks like, and then write a piece of code that mimics it. So in this specific case, it's the simplest because the transpose and complex conjugate of this matrix is basically the equivalent matrix with complex conjugate elements on the diagonal. And so now it's very easy to write 2 different pieces of code. that in this case, we all write it in an object-oriented fashion, but let's focus only on these two small functions. They take a vector x, they multiply with this diagonal vector, and then if you need to apply the adjoint, you also apply the complex conjugate. This is what we do in PyLops, obviously a much simpler version of what we call the diagonal operator. And this is totally equivalent. I'm going to show you with side-by-side snippets of code to what you will do if you were to form the matrix explicitly. If you are a Python user, you will use NumPy or similar libraries, linear algebra libraries in other languages. But basically here, what I show you is that if I have 10 elements and I have a vector that goes from 0 to 9, I can just apply this MP diag to the vector and I will get this diagonal matrix. Now, if I want to apply the forward, I can just apply the dot product between the matrix and the vector. And if I want to apply the adjoint, I need to transpose, complex conjugate, and then apply the dot product. And this is the vectors that I will get as output if the input is full of ones using NumPy. On the right-hand side, this is where the sort of magic comes in. This is the exact same I will get if I have created a PyLops operator and then I use this star or at symbols. And the reason why these work equally well with NumPy or with PyLops is because we both overload this at or the star to basically dispatch the computation to the multiplication or the dot product. And the reason they are equally, the results that you get are the same is because, as I said, you don't need to have a dense matrix to apply an element-wise multiplication. You can do it in a much simpler way with a single operation. That is what I showed in the previous slide. Now, this is the simplest case, but you can think of many complex linear operators like a Fourier transform. You can think of even an operation that mimics CT scanning, an operation that mimics wave propagation, or maybe not properly wave propagation because that's a partially differential equation, but say a ray-based type of propagation. And all of these, you can write them as matrices if you wanted, but it's too expensive to create them and apply them, or you can write them with this paradigm of writing basically matrix-free optimization. Now, with this, you can start building all sorts of flexible applications after you have created a suite of operators that do simpler things, a bit more complex things, and a bit more specialized things. So the first example I'm going to show you, and this is one example. By now, there are 137 citations of our main paper. And if you look in Scholar, I tend to do this for fun every now and then to get some inspiration. You see coming from all sorts of fields, applied to all sorts of problems. And sometimes people discover that there's something missing or something could be optimized. That's also a way for us to get a good feedback. So one example of this 137 that I'm taking comes from us, my previous group in Chaos, because I'm very familiar with it. And it's also a geophysics problem, so maybe some people in the room are familiar with it. This is what what is called nowadays Marchenko-based seismic processing. It's a suite of techniques that were developed from the 2015 onwards that basically use some equation called the Marchenko equations, that are equations coming originally from quantum physics, scattering theory, and basically allows you to estimate how waves propagate in the subsurface, just knowing how they are basically recorded at the surface of the Earth. From a geophysical perspective, this is very useful and can enable all sorts of seismic processing and imaging algorithms. From a mathematics or implementation point of view, this is interesting because it always boils down to solving an inverse problem. And I'm showing you the actual simplest case. There are more advanced versions where the problem becomes even more complicated. And you can see here is that the operator it looks quite complex at first. You have an identity matrix minus this block structure matrix with some zeros here. And you have these R's that is what we call multidimensional convolution operators. You can think of 1D convolutions if you want to make it simple. And one thing that you could think initially is that, okay, this is what I have pen and paper. What I need to do in practice, I need to go down, write a linear operator that implements this and the adjoint. You could do that. The issue is that every time you go to a new problem, you have to start from scratch and rebuild everything from scratch. What we like about this problem is that it can really showcase what happens if you build a library that is modular and has components that can be combined together. So this specific problem, I have a snippet of code with 6 instructions, and actually the operator itself can be built with 6 instructions. We can create these 2 multidimensional convolution operators. We can then combine them together with these windowing operators, that is effectively a diagonal element-wise, what I showed you previously. So that was toy, but actually appears in real-life problems. And then we can create an identity matrix, and then we can combine all of this together in this block structure. You will think this is toy, but effectively this is the same underlying code that we have been using to solve problems of the scale of terabytes on distributed systems, because under the hood is where all the magic happens. At the top, the way you form the problem looks pretty much always the same, no matter whether you're solving it on a laptop or on a supercomputer. And this is just for the geophysicists. This is just an example from one of our tutorials. You see that you can get basically an estimate, the middle panel that is almost identical to modeling if you knew the entire subsurface. And that's sort of the beauty of this Marchenko algorithm. This goes a bit beyond the scope of this talk. The second sort of part that I want to talk a bit about flexibility, is how we sometimes integrate additional things like new solvers. And we don't do it always straight in the main library. We create sister libraries. In this case, this library is called PyProximal. And that allows us to separate concerns and still allow interoperation. And the reason why we want to interoperate is that one could start stacking things on top. The reason why we want to allow separation of concerns is because we're not going to ship a student that wants to start trying with a massive piece of software with a million dependencies. Student can start small and then can add the things as they feel. And if they don't need it, they don't add it. And that's only you can get when you have this kind of modular approach. So what is PyProximal? Is a library, as I said, that sits on top. It simply provides a new set of solvers, or a more advanced set of solvers than the one that most people are used to, are familiar with. So generally, we geophysicists, but also in many other disciplines, are familiar with least square solvers where you have objective functions that are smooth and differentiable. But there's a branch of mathematics that has evolved quite a lot in the last decade. It's called convex optimization. And basically, it extends the idea of smooth functionals to functionals that are non-smooth but convex. Those functions don't have a gradient, but they have something that is a bit the equivalent of a gradient called the proximal. And similar to a gradient, you can write it, in most cases, pen and paper, analytic, and then you can implement it. The beauty of this sort of family of solvers is that they can take any function of this kind, where you have a smooth function or non-smooth, and then a second, definitely non-smooth function, otherwise you are falling back to smooth optimization. The way we implemented this in PyProximal is really to provide users with the possibility to take this generic problem, make it more specific for their use case. In this case, I'm showing you a very simple example of denoising. So simple denoising problem where you want to find a vector x that is as close as possible to the observation, but not identical, otherwise you have not denoised. So you need to add some prior knowledge that tells you what is the extra information that you want your function to behave like or look like. And in this case, I'm making an example with blockiness. I want function or the signal I'm recovering to be blocking. The way you can build this problem is, again, just a few lines of code. We provide what we call functionals or proximal operators for all sorts of norms. So for the L2 norm, this is the first term. For the L1 norm, this is the second term. We then fall back to PyLops for the linear part. So this first derivative operator. And forget about these 3 lines. There's a bit of details about the solver. And then we have a suite of solvers that really take, as I promised before, one function that can be smooth, one function that doesn't have to be smooth, and then a linear operator. So falling back to this f plus glx. And this is an example, 1D, very simple. Dots are the noisy measurements. Black is the real signal, and red is the signal that we estimate. It's not perfect. I mean, it's an impulse inverse problem, but is very good, much better than if you didn't have any prior knowledge, or if you had smooth type of prior knowledge. Again, it looks very simple, but I can promise you we use these kind of things for geophysical problems of the like of seismic inversion or least-square migration or FWI. And in fact, the last slide about biproximal is a summary of 4 very popular family of problems that have emerged in the mathematical community over the last 20 years, and always with a few years gap, has always been used and applied in geophysics. So we have what we call sparse inversion. Most of the geophysicists in the room are probably familiar. So it's a setup where you want your signal to be sparse, so zero, mostly zero, and few non-zero elements. And we tend to do this a lot in geophysics for waveforms. There is also a way to recast these into a matrix form. So you don't want the vector to be sparse, but you want your solution to be recasted in a matrix and have a sparse eigenvalue spectrum. Total variation regularization is pretty much what I showed in the previous slide. Is a problem where you try to get a solution that has some blockiness, some structure. And as I mentioned previously, constraint optimization, when you have some bounds, for example, that you want to run. And this is some geophysical problems that I can think of that we solve for sure in the literature, in various also commercial software with this kind of algorithms. More or less, there is obviously different flavors, but this is sort of a fairly powerful setup where you can solve a lot of problems. All right, how am I going with time? We're okay? Okay, well, let's move on to the last part, which is really about scalability. And this is a brief history in a way about how PyLops evolved. And I think it's also a recommendation I will give to anyone here that wants to build a new software from scratch, maybe a student. Don't start thinking, I want to make everything from day one. You just end up making a mess. Just make something small and then build on top and on top and on top. And that's the only way to make something that eventually will not be a monster. And luckily, I don't think that was my vision at the start. At the start was more just try to make something. But then with time, we really went and progressed with this vision. Don't make too many things at once, just go step by step. So step number 1, what I presented up until now was all built with single CPU in mind. So basically solving these problems on a laptop. So NumPy and SciPy have been always our workhorses for vector containers and scientific operations. And then quite quickly, we realized that there are a few external libraries that are useful. There's no point to implement things that are out there. So transforms like wavelet transform, curvelet transform, that are nice libraries. So we started to wrap those libraries in PyLops operators. So that's the initial setup. A few years after we started, we saw potential to expand these to more advanced hardware, basically accelerator GPUs that were starting to be popular and commercially viable, something that 15 years ago only a major company could buy, but nowadays, at least a small GPU, you could buy it for fun if you want as a Christmas present. So this became useful in a way, and if you don't want to buy it, you can go on Colab. And actually, most of the development of this was initially done in Colab. At that point, the idea was, okay, we want to do that. How are we going to do it? The simplest approach, at least it seemed simpler at the start, it didn't end up being the simplest, was let's just get one of these frameworks that we use for deep learning. Let's just spend of time rewriting some of our code, and then we are in business. It turns out that a lot of code needed to be rewritten. Some of those libraries at that time were not really mature when it comes to scientific routines, like they were lacking FFTs, for example. But there was a little kid in the room that was starting to also appear called CuPy. There was a library built actually by a Japanese company. And their promise was, we're going to replace one-to-one NumPy. So anything you do in NumPy, you would just be able to do it in CuPy, importing CuPy instead of NumPy. So that was a bit different from the PyTorch or TensorFlow that they basically said, we depart, we do it our way, and you follow us. And we thought it was a good idea. We started to prototype. Didn't turn out that you just change the import. That would have been too nice. We needed to do some smart tricks inside, but that required, I would say, bottom line, little code, little extra code, and gave us an API that is fully interchangeable. So we could do this kind of test to begin with to see if the idea of using GPUs was useful. I have a EAGE abstract on this for more details if you're interested. This test simply takes all the operators that we had at that time in 2021, runs them on the CPU and on the GPU with an equal size, and compares both the for and the adjoint. And what I have in the y-axis is the speed up. So what you can see that if he's below the gray box means he's lower on the GPU, if he's above means he's faster. And you see that the only operations that actually is lower are those that require only memory allocation, that we know is expensive on GPUs. Anything that is sort of a CPU type of operation is generally 10 or even 100 or even more faster. And this was a GPU in 2021, a fairly powerful one in 2020. Nowadays, we have even more powerful GPUs. So with this comes the second step. Okay, we give you something that is faster, but if I tell you that now you have to take everything you have done, spend a month rewriting it to get that performance, that may be okay if you are a company with tens of developers, not so much if you're a student, you just want to do this to get your codes a bit faster. So really the idea that we had since the beginning was we want to allow, or we want to have the minimal number of required code changes to jump from one to the other. And I'm taking again the exact same example that I mentioned at the start, a convolution type of example. And this is what you will do in the left-hand side with NumPy, so our CPU backend. This is what you will do with our GPU backend. And in black is the only code changes you need to do. Pretty much all you need to do, you need to make sure that the data moves to the CPU, either by taking an NumPy array and lifting it to the GPU through this CPS array, or by building it directly with CuPy. And finally, this is the nice part. The way you create the data, so the way you apply the operator or the adjoint remains completely unchanged and transparent to the user. And then the way you solve the inverse problem, you need to switch to PyLops solvers, which are basically one-to-one replacement for SciPy solvers, because SciPy does not offer a GPU backend. But that's pretty easy. It takes you a couple of minutes to do it. If you want to do it well, you need to make sure that you stay in lower precision, something you sometimes don't care for early prototyping code. So it will take a bit longer, but this is the philosophy. Don't want too much code changes. And this is one example from a real-life geophysical problem. If you're familiar with seismic inversion, this is basically a bunch of 1D convolutions because it's a sort of trace-independent type of operator. We have done this on the Volve data. This is subvolume of the Volve data with these dimensions. And at that time, it took 43 seconds to run on a CPU with NumPy. It took 3 seconds to run the GPU. I'll come back later with this example with more. Now, again, as I said, step by step, we got to a point in 2022 that we thought we have a good setup, but again, we are limited to a single node setup. It's a laptop, a big workstation, but no more than that. There are problems that either they're too big, you can't really fit everything in the memory of the single node, or they are naturally embarrassingly parallel in some parts of the operator and the inverse problem. So we thought it was a good time to start thinking about how we extend this library to scale to multiple computers, so have a distributed sort of backend. And we had this project through Google Summer of Code. That was sort of a vital support. Google has this very nice summer project that if you submit a project with an open source library and I think it's good enough, and you find a good enough student, that will finance the student for the summer and they can work on your project. So Rohan was the student that we picked out of quite a bit of selection. And initially we thought everything can be done in PyLops. We quickly realized again, it was a bit too much. Created a sister library called PyLops MPI that again sits on top, interfaces nicely. But if you're a student, you don't want to do distributed computing, you don't need to go through the effort of installing MPI and all the Shigan around it. You can just start with small PyLops, later move on if you need. Now, how much do I have left? I lost track when I started. 40%. Yeah, so when did I start? Okay. I can do 5 minutes. Let's do that. Okay. All right. So where do you see inverse problems being distributed? There are two scenarios. So left scenario is where you basically see that you can separate your model, you can separate your data, and distribute it across as many works as you have. They never talk to each other than in the solver. That's a fairly simple scenario, but there are many problems that are sort of embarrassing parallel at the operator level. There are then other problems where you don't separate the model because we can keep it in the same machine, it's small enough, but the operator is too expensive, so you can separate the operator in parts and run each individual part of the operator on different ranks. Now there is a bit more communication to do because in the forward pass, there is no communication. With the join pass, you basically, each rank or worker has to compute one version of the model, and then they all have to be summed together. And again, there could be some communication in the solver. So these are the two scenarios that we wanted to tackle. And the way we built PyLops MPI was basically a one-to-one mirror to PyLops. So anything that we had in PyLops, we added an MPI in front and provided an MPI extension. So as I mentioned previously, we have things like this block operator that allows you to combine multiple operators in a block fashion. You can stack them vertically, you can stack them horizontally. And this is the kind of operators that we needed to build because they require all of this internal, basically, communication. We also needed to build something on top of NumPy because NumPy is a great library, but provides you vectors that sit on your RAM. We needed distributed arrays where the container has knowledge that the same array is partially distributed across multiple ranks, and things they need to be cooperating in different setups. Like if you do a norm, you need to do partial norms, and then you need to accumulate the norms. We put these to test. Since I don't have much time, I'm gonna send you to this Medium blog post that I wrote last year, showing what we call the 4 levels of parallelism of PyLops. So we took again this seismic inverse problem. Now we took the entire volume, and we decided to do this with this problem because it's embarrassingly parallel on the operator, but you can couple it with a regularizer like smoothness constraints, and then it's coupled in the solver. And as I said, we started the journey that I would suggest everyone to do if they want to solve a problem in PyLops. So first, run it on a single CPU, small, make it work. Switch to the GPU, again, make it work, make sure it's performant. Then bring in the multi-CPU option, and then switch to multi-GPU. And so while the code grows a bit, what I want to show you in the next 2-3 minutes is that it doesn't grow massively. So this is really the entire piece of code for the single CPU case, where you build the operator and the regularizer, and then you solve it with a solver. This is what happens on the GPU. I already mentioned this previously. The changes are tiny. They're basically making sure that all these NumPy arrays are now moved into the GPU, so they become CuPy arrays. The bigger step is to go from single CPU to single or to multi-CPU, because again, as you'll see in a minute, from multi-CPU to multi-GPU is, again, a tiny change. You just need to make sure everything's lifted to the GPU. But don't look at the code, just look at kind of the overall idea. The first part is pretty much understanding how you distribute the problem. Then the most interesting and most important part is the creation of this distributed container that you fill now in each of your ranks with your NumPy arrays. Then you create the distributed operators that, again, are just basically a combination of PyLops operator where each rank will take care of part of it. And then you have naturally solvers that are one-to-one equivalent signature in a way of your function than the one you have in PyLops, and now they have this knowledge of distributed operators. And for the GPU, as I said, the only change is just making sure things don't go on GPU. We did many different tests with the hardware that you see here, and the bottom line was, if everything fits on your GPUs, going from single CPU to multi-GPU, so the extreme cases give you a 50x. If they don't have enough GPUs and they don't fit, you need to do quite a bit of movement of data in and out. They still give you a 5x. So that motivated a few extra developments that we are doing. One, trying to be clever in the way you move data in and out of the GPU. And the other one, which I'm gonna spend 1 more minute, is try to be smarter, or not be smarter, but try to provide a new way to communicate if you're working with GPUs that is not relying on MPI, but is relying on this a new library called Nickel that NVIDIA has developed, mostly used for deep learning these days, to be as efficient as possible when you communicate between multiple GPUs. It's not that straightforward to do, so we led a new Google Summer of Code project that we had this year with this smart student called Tarit. I did a lot of work, and the bottom line is in this plot. You can gain a lot from going from MPI to Nickel. So this is the time it takes to communicate. So it gave us a lot of motivation, and we are working now. We are starting now to have the first mature version of the code, and we'll report in the near future how it performs. But the last thing I want to kind of show you again to bring home the message is that we follow once again the same paradigm. If you have a code on the left that you're confident and works with PyLops MPI, switching to Nickel is again a matter of few lines of code changes, creating a Nickel communicator, and then again making sure you pass through PyArrays. So again, from a user perspective, we're already very happy. We think that the switch is again almost seamless. Now we want to also be happy from a performance point of view, and that's where we are now. I'm going to skip a few slides. I'm going to leave you with some resources that pretty much document everything I said in much more detail. I want to acknowledge and thank. I do it for myself because other core developers said if they present, they do it for themselves. We don't want to do it for each other. So I'm only thanking the 3 employers that I've been working with throughout the years of the development of PyLops, but there are many more companies that allow people time and resources. And of course, Google for Google Summer of Code for supporting 2 projects, and NumFocus that is for quite a few years now supporting PyLops as an affiliated project. But you can't do much with just organizations. Usually code is written by people up until ChatGPT. And so I also want to thank all the core developers, maintainers, as well as contributors that may have contributed a line of code from a bug to hundreds of lines of code with new operators on new solvers. And thank you for listening. I'm happy to take any questions.